Okay, today I'm going to first show you, we have some shaders, some example shaders. I have written a viewer for PLI format meshes, which can also be, they can be, I created these meshes with the help of this Mesh Lab. Although Blender is a really nice tool to create meshes and work around with them to create scenes. Blender is also freely available. This Mesh Lab is very lightweight. It supports different formats, and you can also do some simplification type of things, mesh simplification. You can convert different formats, and therefore I downloaded some meshes from TurboSquid and created them to ASCII PLY format by using this Mesh Lab tool. So for example, when you say import mesh, you can, there are some sample meshes I have here, which can also, you can either download sample meshes that comes with Mesh Lab, or you can, for example, there is chameleon points. So this is, I think, like a point format. You can have point clouds, you can triangulate them, you can then convert to different formats. So this is what I did, and I have some example meshes here that I'm going to show you. I got this Formula One car, for example, from turbosquid.com. It was an FBX file format. Then I converted. FBX has some MeshLab has some problems with FBX file format. I couldn't convert it there, but Windows comes with its own 3D Paint tool. You can open FBX files with it and save it as something else. So I did some conversion between these different file formats. But at the end, I was able to convert them to ASCII PLY file format, which looks something like this. Okay, so the ASCII format is really simple. It lists certain properties. Actually, I just ignore the header. The only thing I get from the header is the number of vertices and the number of faces this file has. And these properties actually indicate the first three values here are the coordinates. The next three values are the normal vectors, normal for that vertex. So the normals are pre-computed for me for every vertex. So that's really nice. I don't need to do any normal computation. And the faces come afterwards here. It indicates that the face is a triangle, and these are the indices to the vertices at the top, which start at index 0. All right, so this is a very simple format, and they're readily available to read and send as vertex buffer objects. These are my vertex data, normal data, and my index data as integers. So I'm going to show you a program, and I'm going to share this program with you today, how to visualize any PLY file like this by using an OpenGL program and with the help of different shaders. I had written a Fonk shader for this. It's very simple. There's just one directional light source, which is hard-coded in the shader. And the program itself is really short. I mean, it's only like 300 lines of code, including all the template that contains reading. I'm going to show, well, we have went over these shader initialization code before, how we load shader, read shader as from our text file, then create these shaders by using GL create shader function calls within the, so GL shader source, GL compile shader, all these are, since I'm going to share this source code with you, you'll be able to use these exactly like this in your fourth assignment where you're going to be writing some simple shaders. So this read shader reads the file and creates this string, nothing more, and loads init shaders. Then each shader is attached to our program that we are going to replace the fixed rendering pipeline. We link the program, combine these two shaders together, and when I say GL use program, instead of the fixed forward rendering pipeline, my program is used. Okay, so it's really easy. Reading the PLY file is also very simple. So this is the read PLY that I had written yesterday. It parses the PLY file. So when the line header line starts with element vertex, I get the vertex number of vertices from that line. I get the number of triangles from that line. And I create my vertex data, normal data, which is 3 coordinates per vertex, 3 coordinates per normal. And as the index data is 3 integers per triangle. So these are just the data that I'm going to store in memory, and then copy all this vertex, normal, and index data to the GPU. And here is after I create these, I read them from the file. So 6 floating point numbers are read to vertex data and normal data. And also I maintain here, so this piece of code is used to automatically place the camera so that the entire object is within the field of view. I wasn't able to get what I exactly wanted actually. I mean, you may feel free to modify this code so that it's really in your center of field of view. My goal for this code was just to find the bounding box of the object. So this minimum x, minimum y, maximum y, by using the vertices, I actually check whether I just find the bounding box, the boundaries of the rectangular box that encloses the entire object, entire vertex coordinates inside it. I use this min x, max y to find some. I use the midpoint of this min and max as the center of the object. I don't actually compute the center of mass, but the midpoint between these two things, I use it as center, which is not correct. But anyway, so you may actually have better things to do to get this bounding box entirely in your field of view, centered at the field of view. So I read the triangle index information, and that's it. This is very simple, actually. At the end, if you look at the main program, I sent to the GPU 3 things as uniform variables. My model view projection matrix, I send it to the GPU. The modeling matrix only for lighting computations. I don't want to do projection transformation. In the world space, I need to deal with the lighting computation in the world coordinates. Therefore, I also send the modeling matrix before it's multiplied with the projection matrix. I also sent the location of the camera, which is the eye position that is used to compute specular component of the lighting. Because if you remember, in the specular component, we have this to-view vector or eye vector that we need for the specular shading. That's why I also send this information from the CPU to the GPU at every frame. So in the way they are sent are like this. So if you look at the rest of the code, we read the PLY file. We generate our vertex buffer objects, 3 of them for the vertex information, normal information, index information. You can also, for example, another common buffer that you create is, for example, for texture coordinates. Texture coordinates are just like normal vector attribute of a vertex. A texture coordinate, which is a 2-dimensional floating point vector, is also an attribute of a vertex, and you can have a separate texture buffer object if you're going to do. We are going to see texture mapping in OpenGL today, so we usually generate another buffer for texture coordinates. By the way, all these vertex, normal, and index information can also be in the same buffer object, interleaved, okay, one after another. But I prefer to keep them separate. I don't know, maybe it may be a little bit less efficient than keeping them interleaved. But keeping separate is easier to code. I just bind each buffer and copy the data to the GPU. So here the vertex information is sent to the GPU, the normal information is sent to the GPU, the triangle vertex index information is sent to the GPU, and then the buffer is bound to nothing with this. It's like resetting everything. And then here, my CPU memory is freed. All the vertex normal data is freed. And the shaders are red, vertex and fragment shaders. I enable these client state, enable depth tests. I disable backface removal. The reason for that was the elephant model that I used, the ears of the elephant, they contain very thin triangles. There was some, I still have the problem with elephant ears. You'll see what I mean when you see the elephant. But yeah, even this GL disable call face didn't work actually. I still have that. So in order to send some variables from the CPU to the GPU, we call this GL get uniform location function, which gets the variable name MVP from the shader. For example, let me open my Fonk shaders, the vertex shader and the fragment shader. Okay, so it's both of them are like one page of code. Actually, this is like half pages. You see these variable names, MVP, M, and Campos. These uniform variables. This one is a 4x4 matrix. This one is also 4x4 matrix, and the camera position is a three-dimensional vector. These are these variable names. The way to assign something to these variable names is to first get their location as integer handles, because as GPU and CPU are different entities, a variable on the GPU, we don't have a pointer to that directly. Okay, the only way the CPU accesses elements on GPU are with these integer handles. And this MVP location is nothing but an GL unsigned int. It's an unsigned integer basically, but it's going to be used as a pointer, as a handle to this MVP variable. So we get there, this get uniform location will help me to get a variable with this name from MVP location. You may ask, for example, what happens if in the shader there is no variable named MVP? I think you just get, the program doesn't crash at that point. The good thing is that, yeah, I mean, if you, for example, make a mistake and write something like this, get this variable name, the program doesn't crash. You don't get a runtime error. It just gives you a handle, which is like indicating a null pointer or nothing that name exists. And when you try to send data to that nothing position, no runtime error occurs actually. The GPU for the programmable shader just ignores this. Okay, so that's a good thing. So you get these locations, and I use the linmath library for these GL translate, look at, projection things. I could have also used the GLM library. So this linmath contains some matrix vector, some OpenGL related functions like perspective, GL look at functions are implemented in that, matrix multiplication, things like that. And it has a mat 4x4 type in it. So these are my mat 4x4 types. I have the MVP matrix, modeling matrix multiplied by the viewing matrix, the modeling viewing matrix. This is the projection matrix, and this is the modeling matrix only. And this is some temporary matrix. This is the camera matrix. So I just multiply them with each other to get the final MVP matrix. My camera position, camera setting, camera up. So as I told you before, the center of the object I treat it as the midpoint between this bounding. The center of that rectangular box, I treat it as the center of the object. It's not a bad idea actually. Yeah, it's exactly the center of the rectangular bounding box. So look at this, for example. The mat 4x4 perspective function from linmath directly creates a perspective projection matrix with these parameters, which is the same parameters as GLU perspective. 45-degree vertical field of view angle, the aspect ratio, the near plane, far plane. With these parameters, it creates a 4x4 matrix and stores it inside this P. Now I bind my buffers to indicate these are my normal data, these are my vertex data, and these are I'm going to be, the last thing I bind before I exit this bind buffer thing is the index buffer, because I will be using the draw elements function to draw everything, and bind buffer is going to have this, the final thing that is bound will be the index buffer. Okay, now I clear my entire screen. Now we're inside the while loop, as you can see. I can put this outside the while loop because P doesn't change here. Oh, but the reason I put this inside this while loop is that this ratio can change. If I resize the window, ratio is going to change. So I have my perspective automatically updated if I have a different window aspect ratio. So whatever the aspect ratio of the window is when it's resized, I'm going to change my perspective according to that. That's why I put this inside the while loop. So this handles the resizing of the window. And my camera, I put the camera in this strange position, and it's looking at the center of the bounding box. Its up vector is 0, 1, 0. This camera position, I tried different things. This seemed to work best, but yeah, you can do different things at this point. And this look at function nicely creates a V matrix with the GLU look at parameters. And here I do some rotation. In order to first, I wanted to rotate the object around the y-axis, okay? With certain degrees, but before rotating around the y-axis, I translate the object first its center of the bounding box to 0, 0, do the rotation, translate back. So the idea here was to rotate the object around the bounding box, but somehow it does. Maybe I'm doing there may be some bugs in this code, by the way, because it doesn't work as intended. The objects doesn't seem to work around the center of the bounding box. Maybe the center of the bounding box may not be the center of the object itself. That may be one of the reasons. But yeah, the rotation is not as I expected. So, and I multiply these matrices with each other, multiply the modeling with the viewing matrix, to get the MV matrix. Then I multiply the MV matrix with P matrix to get the MVP matrix. And these three function calls send the camera position, the M matrix, modeling matrix, and MVP matrix to my shaders. And then I just draw my object, and that's it. Okay. So as you can see, the only thing that is animating dynamic here is this rotate, which gets the current time, GLFW get time, to perform a rotation of the object. So let's see how it works. All right. So before how it works, let's try to go look at our vertex shaders quickly. I have a number of vertex shaders here. The simplest vertex shader you can have is this one. For example, in this one, there is no M or campus. So those variables actually are not sent here, because since I don't need them here, I'm not going to do any lighting computations. I just need the model viewing projection matrix. So the program doesn't complain when the GL get uniform location cannot find the variables named M and campus. Okay, so it's just sent to some random position on a null place where it's not going to be used. So this is the simplest vertex shader you can have, and the simplest fragment shader you can have is this. Fragment color is equal to 1, 0, 0, 0. Okay, this is red. So if I run this, let me go ahead and run. I call it PLY view. So it gets a file name. For example, let's look at this Formula 1 car. And let's use the simple vertex shader and simple fragment shader, what it does. So when you run it, it runs and it's like this. Okay, so this is that Formula 1 car. So we can see its silhouette nicely, but any fragment that is mapped onto the screen is gets to color red. Okay, when there's no color computation, all your fragments are red. This is what you see. But what always also you see is that all the vertices are nicely in perspective projection. They are mapped, so actually you're seeing something. It's not just black screen. The only thing is that all the fragments you have are exactly red. Okay, now if we do the Fonk shader, so we have now, let's look at Fonk shader. What do we do in Fonk shading? Fonk shading is normal interpolated color computation. In other words, instead of computing color per vertex, I can also, an exercise you can do, for example, is to convert this Fonk shader code into go-route shading code, which the OpenGL does by default in the fixed forward pipeline, which means that instead of computing the color that here, so this color is computed here as an addition of ambient, diffuse, and specular. Instead of putting everything here, compute everything in the vertex shader, your color, and define your color as a varying vec4, which is going to be interpolated. So compute color here. What I mean is that color is equal to something. You do it here, okay, ambient plus. And if you specify it as a varying, all you need to do in this shader is going to be saying that GL frag color is equal to color, and that's it. So, and when you have a varying vec for color, it will be automatically interpolated. All these computations you have here, you can copy those into the vertex shader part. That's go-route shading. That's gel smooth shading that we normally have by default in OpenGL. Okay. Now, instead of doing that in Fonk shading, you can, if you want to see the similarity differences between go-route shading and Fonk shading, it may be interesting to have to write that shader, and it will be a very simple exercise for you to do that. So instead of having that, in the vertex shader, what we do is we actually define the normal vector as something varying and position as something varying. Position, this will be the fragment position because we have the coordinates at the vertices. But when we have a fragment, we also need its exact position because of using its exact position, we are going to compute the specular component better. So since I don't have any non-uniform scaling, the 3x3, the first 3x3 part of the modeling matrix can be used to transform my normal vectors. So this GL normal, GL vertex is coming from those vertex buffer objects that I specified. It gets this information from there, and normal and position is set as varying variables, which I set them here first, and whatever value I give to these normal and position variables, they are going to be interpolated for every fragment within a triangle. So the computation is done per vertex right now. Normal and position are multiplied. These matrix multiplication is done per vertex, and whatever value I assign for the vertex for a triangle, the fragment's normal and position will be an interpolated value of S3 of the three vertices. And this gel position, which is the position of the fragment on the image, is computed by, it's also depth. Depth is also computed here because since we enabled GL depth test, the depth of the fragment is also found after this model view projection matrix multiplication of a GL vertex. Okay, so that's the minimum thing that I do in a Fonk shader and Fonk vertex shader. And then if you look at the fragment shader, it doesn't need the MVP. It just needs the modeling matrix. Maybe it doesn't even need the modeling matrix. Why do I need the modeling matrix here? I don't use it because I already have the normal and positions here Probably I don't need that, but anyway, having that defined it as an unused variable, it doesn't hurt actually. What I first do is I make my vectors unit vectors in case they're not unit. To be sure, I convert them to unit vectors. And here, my light vector, as you can see, is something constant. In other words, I don't have a point light source in the scene. I have a directional light source. And this is the to light vector. So light is actually shining in 1, -5. So from top, so -5 is y coordinate down. So somewhere light is directional means that it shines in every direction at every point. So it's like as if we have a light point light source at infinity, which has this vector for every point in our scene. This is my light vector. So I just specified my light as something constant, hard-coded in the Fonk shader. You could have also have this sent as some variable from the CPU side, just like we are sending the camera position. We could actually send the light position from the CPU to the GPU. This may be some user input that you get when you start your program. My V vector is the position minus camera position. So this is where I need the camera position. And so this is the 2V vector. And what I do is, why do I multiply this with minus? So position minus, so it's to the position. So I could have written this campos minus position. So this is the to I vector, to light vector, and this is my half vector. Diffuse is simply the dot product. So all these functions, dot, or creating new vectors, they are built in GLSL. We get the dot product. If the dot product is less than 0, I want to ignore that. This is why I use this max function. So get whatever, if the dot product is less than 0, just treat it as if it's 0. This is what this max function does. And I multiply, oh, look at this. This is my reflectance coefficient multiplied with light intensity. Also, this is also hard-coded. So my material information of the surface, the diffuse material, is also some red-green, so kind of a brownish color. So a little bit blue, half green, and lots of red. Okay, we'll see what kind of a color it is. And this is alpha value, which means that it's non-transparent. My ambient is gray, 050505, and my specular is white light, and I multiply the normal vector with the half vector. I take the dot product, and my specular exponent is 50. So all the material related information, light intensity, light color, everything is currently hard-coded into this shader. As I said, you can take them as uniform variables also coming from the CPU side. And at the end, all I do is add whatever you compute as ambient, if you specular, add them up and clamp them to, if they are larger than 1.0, clamp them to 1.0. If they are smaller than 0, again, clamp them. So everything should be between clamped. If they are larger than that, just get rid of the rest. Everything, the value should be between 0 and 1. And this clamp function is also nicely available to us as a built-in function that we can use. And at the end, we just set the fragment color to this clamped color, and that's it. It's only like 10, 20 lines of code. So let's see how the Formula 1 car is going to be visualized with this Fonk shader. Vertex shader, and I didn't compile anything, and because these two vertex and fragment shaders are going to be read on the fly. So here's how it looks like, much better than the red thing, right? So here's that all red, and so the specular spot, they are moving along with us. It's like the camera is moving around the car. Actually, the car is not moving. So the effect is, if the car was moving, the light direction would change, right? Because the bottom of the car is always dark. So it's actually, the car is not moving. It's the camera that is moving around the car. You should think about it like this. Any questions at this point? So as you can see, it's the specular. They are dynamic because the viewpoint changes, um, and so this is, we get nice diffuse shading and specular shading. Let's look at the elephant. Now let's look at elephant. So this is the elephant. Yeah, look at the ears. The ear triangles have some problems. The mesh lab also viewed the ears like this. But if I changed some setting to view the triangles both from back and front, this actually was solved. So I thought the problem was related to back face culling here. But even if I disable back face culling, it's still like this. I don't know. The ears of the elephant looks bad. Now, I'm going to show you some other shader before I continue with the slides. And as I said, I'm going to share this code with you. You can play with these shaders. There are really fun things you can do. Now I'm going to show you one fun thing without changing. I will be using the same vertex shader. I'll just change the fragment shader to something else. We also have different models. I'm going to also share all these models with you. We have a hippo, I think. Yeah. Yeah, so this is again, the specular spots are nice. There's some black thing here due to some rectangle, maybe, I don't know. And if you look at this model, for example, the hippo model, it looks really smooth. It seems like there are lots of triangles on it, right? I mean, it seems pretty smooth to me. But if you open the same model in MeshLab, you'll see that it contains very large triangles, actually. Import mesh, go to this PLY view. This is the hippo. You see, you can actually see the triangles. So this is in flat shading. It appears like this. Yeah, actually, you see that vortex? It's also here. It's not my program's bug. The mesh has a bug in it. One triangle is missing. Interesting. One triangle on hippo is missing, and we could see that missing triangle also in our viewer. Yeah, that missing triangle. I don't know whether you can see it in this video or not. Maybe in the recording you will be able to see better, but there's that missing triangle. But in Phong shading, as you can see, that nice smooth shaded model. So this is normal Bayes interpolation. As I said, as an exercise, you can do Gouraud shading and put them side by side to see how normal Bayes shading changes things. Now, here's the interesting thing. Let me first show you the shader, and you're going to appreciate how these little changes produce really interesting and nice effects. So this is called gooch shading. Okay, it's like non-realistic, cartoonish shading. So there are three colors: bright color, dark color, specular color. So these are high, low, specular type of thing. We get the normal and position and the camera position, just like Phong shading. It's like normal Bayes interpolation. We normalize our normal, we get the I vector, we get the light vector. I use the same light direction as the previous one. So very similar to the previous Phong shader. Okay, now, but we have some interesting masks. It says that if the dot product between the edge I vector and the normal vector is greater than 0.4, so it's like the specular. Use 1 or use 1, otherwise 0. So it's like there are hard thresholds. In Phong shading, everything was smooth. We didn't have these hard thresholds when setting color. So this edge mask is saying that if your specular is only, if the dot product is only greater than 0.4, use it as 1, otherwise use it as 0. Okay, so a hard threshold. So, and this is our half vector, and this is the specular mask again. We take, this is my specular exponent. If the result is, again, everything is either between 1 or 0. Okay, so there are hard thresholds in my color. and also the dot product between the light vector and normal vectors. This is the diffuse color. Even the diffuse color, there are hard thresholds. If it's larger than 0.4, use it as 1, otherwise use 0. Okay, so everything, the color at the end is defined as this low color, high mass mix. So we mix these things. So there's a mix function. I didn't know this. So I didn't write this shader myself. I found this like 7 years ago in some shader examples. I just use some other code from some example shaders. Okay, so I'm not the author of this shader, but let's just see how the result looks like. Let's start with the hippo. Just I'm changing this font to this Gooch fragment shader. Look at this. Cool, right? I mean, it's really like cartoonish. The formula, it looks really better in the formula card too. So there are maybe lots of black spots. It doesn't look that good maybe. Maybe for the Formula 1 car it may look better. Yeah, look at this. It gets a nice cartoonish rendering. Just if you're interested in, for example, to provide some animation that looks cartoonish, this is the shader you should use, or you can modify this to provide other shaders. So this is the power of programmable shaders. You can get any visual effect you want. All these specular exponents now, they are, because of these hard thresholds, no smooth thresholds, it gives it a cartoonish feeling. All right. So I'm going to share all these shaders and the models and this program with you, and you can play with it. You can try different settings. All right, so that's all I want to talk about programmable shaders. Now, in the last 10 minutes or so, I'm going to start the new set of slides, texture mapping and frame buffer objects. And on Thursday, we are going to talk about how to implement shadows in OpenGL with the help of these frame buffer objects and using depth buffer as a texture object. Okay, so the first part of these slides, any questions, by the way, about the previous, either the code or the GLSL shading language? I hope everything is clear, but let me know if you have any questions, okay? So this texture mapping, we have already covered these slides when we were doing ray tracing. So we did texture mapping in ray tracing, so we know how to map a two-dimensional image, the UV coordinates that are between 0 and 1 to objects. So we parameterized an object surface, basically. We parameterize it to these, as if it's a two-dimensional manifold. We give coordinates between 0 and 1 to the object surface, and we assign texture coordinates for every vertex of the object. In ray tracing, this mapping actually was continuous. For a sphere, for example, any point on the sphere, if we know the coordinates, we were able to map that thing to a UV coordinate. It also not only for spheres, for triangles too. If you know a point inside the triangle, if you know its coordinates, by using the texture coordinates of its vertices and by using barycentric coordinates, we were able to get the texture coordinates of that fragment within the triangle. Okay, so these are the things that we did earlier. So I'm going to skip these parts. So we have used nearest neighbor or bilinear interpolation. We have seen the difference between those two things. And we can map images to our geometry. This is what we did. Now, the important part here is how do we do texture mapping in OpenGL? In OpenGL, I'm going to share on Thursday with you this Martian Rux source code, which maps 3 different textures to the 3 different objects. So if you Martian Rux. So was it? So let's see. We actually. I was going to use this to Martian Rocks txt4 to show you fragment shader, font shading on last Thursday. But then I decided to write a program from scratch. This PLY viewer, I replaced this Martian Rocks we are going to render. So yeah, if you run this, you see the rocks left and right are mapped with different textures, and the zebra itself is mapped with different textures. So I'm going to share the source code of this with you, and this doesn't use any shading at all. Okay, the specular looking like things on the texture is exactly the texture color as it appears. There is no lighting, no shading computation here at all. The entire vertex colors are taken from texture coordinates. And as I said, I'm going to share this code with you on Thursday, which contains this texture-related code. The way OpenGL automatically provides you a way to sample pixel colors from a given texture. So you can, in order to use texture in OpenGL, we create a name for our texture. Again, everything is like with integer handles. Just like we generate shaders, we generate vertex buffer objects. We have unsigned integers that we name sampler and texture. A texture is the two-dimensional image itself. A sampler is a function. It's like an additional utility in front of a texture that allows you to pick colors from that texture. For example, your sampler may be using bilinear interpolation. Your sampler may be using nearest neighbor texture picking. So all the mechanistics of how to find the color from a texture image is actually separated from the texture itself, and it's put into an object named sampler. So that's the purpose of sampling from texture. And as you can see, these parameters, whether we are going to get the nearest or the linear interpolation, whether we are going to wrap, if the UV coordinates are outside the 0-1 range, how do we treat the texture? Do we repeat the texture, tiling, or do we clamp the final edge value? Things like that are sampling parameters. And by using GL sampler parameter I OpenGL functions, we can set different things. So these are like texture minification filter, magnification filter. Minified means that if your texture is going to be mapped to a location that is actual to a geometry that is actually smaller than the resolution of your texture, what do you do then? And if you try to map your texture to a larger region, how do you combine different pixel values into a single pixel value? So these are different texture parameters that you can set on your sampler. And then you bind your sampler to the desired texture unit. So texture unit 0 is the current, by default, the extra texture unit. So there are different texture units which allow users to apply actually multiple textures at the same time to a single surface. So this multi-texturing is not the same as having 3 textures in your program. So what I have here is not multi-texturing, okay? Because a single texture is applied on a single surface. So all I do is changing the current active, when I'm rendering the rug, I'm changing the active texture to some other texture image. Multi-texturing refers to the fact that you may have multiple images that you might want to map onto the same surface. Okay, in that case, there may be different texture units. That's the only case where you're going to need more than one texture unit actually. Otherwise, texture unit 0 will just do fine. And so the active texture is this: you activate your texture, you bind your texture to your texture buffer object. So you activate desired texture unit, and you don't need to memorize all these stuff, by the way. Okay, all these OpenGL function calls. Again, these slides like API reference. That's why I'm not going to spend too much time on them. And since I'm going to provide you a sample code, texture mapping code on Thursday, you may also use the existing code given in the example. But just these slides show what these different functions are for, their purpose. We can also, when you're reading the texture image, the RGB values in it, they may have different packing of values, whether interleave or not. So we need to call these functions to indicate those things. Some textures may contain also transparency information, whether it contains RGB or RGBA, we indicate here. And this GL text image 2D is the same function as this GL buffer data function we use for our vertex buffer objects. So this is the function that copies the texture image to GPU. So by calling this function, we copy the entire texture data to some texture object on the GPU. And here's the relationship between all those things. We actually have the image from our file. We read it. We first read our image if it's in PPM format. This is what I had in this Martian texture example. All of them are PPM format because it's easy to read and store them into one-dimensional, two-dimensional arrays. So this part, the programmer is responsible by using either a libjpeg library. If you have PNG textures, you need libpng to read those images. So we need an image reader first to read those into our CPU as 1D, 2D arrays. Then we copy them to texture units on the GPU. And usually, if you're not doing multi-texturing, and this is just a pointer. The texture unit may be actually pointing to different texture buffer objects, texture objects on the GPU. And the sampler is going to sample from this current active texture unit. And the rest is, after we set up our texturing, the rest is we need to provide, just like we provide normal vectors for each vertex. For each vertex, we provide UV coordinates, texture coordinates. There's an OpenGL function for that in immediate mode, just like GL vertex. The GL text coord 2f, before the call to GL vertex, if you call this function, it will assign UV coordinates to that vertex. And using vertex array, we should provide the texture coordinates also in an array, just like it's very similar to providing the normal vectors. And when we are using vertex buffer objects, instead of calling this GL text coord 2f function for every vertex, we just say this is where texture data is. My texture data is in this array, and I just say that I just give a pointer to the texture data. And this, just like I did in normal pointer, GL normal pointer, GL text coord pointer, or GL vertex pointer. These are the functions that we tell OpenGL what kind of data is residing in which place. In the newest version of OpenGL, in the core profile, all these texture, vertex, normal, they are treated the same way as generic attributes. There is no text. This function probably is deprecated in the core profile. The newest OpenGL, for example, GLSL 330, we may not get the texture coordinates with these. Probably they become attributes, general attributes. But we will be using the older version of the GLSL, which we have these as built-in variables because it's really convenient to access the GL texture coordinate from our built-in variables. So this is in the vertex shader. This GL multi-text coord 0 is just like this GL vertex. Whatever UV coordinate associated to this GL vertex, that those coordinates, UV coordinates, will be available here in this GL multi-text coord, and we pass it to the rasterizer by setting this built-in variable. And this built-in variable GL text coord 0 is automatically interpolated. You don't need to define it as a varying variable. And this is the vertex color. If the vertices have different colors also associated with them, you can also use this gel color built-in variable. And our sampler, a uniform sampler to the my sampler, we just set from our CPU program. We give it sampler texture unit sampler location. This variable represents the texture unit index. It will, since if we're not doing multi-texturing, we will just be using texture unit 0, and therefore from the OpenGL site we send, in terms of this my sampler, we sent the value 0 to this. And this texture 2D function is a built-in function again that allows the sampler, which has some associated parameters. Also, the sampler here contains parameters like whether we are using bilinear interpolation, nearest neighbor, things like that. And this is the UV coordinates are also named as ST coordinates here. These will be the interpolated texture coordinates. By using the sampler, it will automatically get texture pixel values, pixel colors from our texture, and we just set the fragment color directly to this. So this is just like in this Marty and Rux example. This is the way to completely replace the fragment color with a texture color. Sometimes we want to use this texture sampler texture 2D. If you remember, we were using in ray tracing as the diffuse reflectance coefficient. So we can actually have a nice light source here. Some part of the Marty may be darker, some part of it may be lighter. So we may have a light source, a point light source, and illuminate the environment with nice lighting and with specular reflection. And for that, whatever we get from this texture 2D, we can use it as our diffuse reflectance coefficient, and then use that in our lighting model to get nicer quality texture mapped scenes. Okay, actually it will be nice if this PLY viewer that we have seen here, for example, if this was texture mapped, it will maybe even look even better. All right, so we can also do texture mapping on this PLY viewer. And at this point we have this picture, and we can by the sampler to different texture unit location, we can have our sampler to point to multiple textures that are here like this. As I said, this is the part where we can blend the interpolated color value with the texture color. So this color actually may not necessarily be constant color for a vertex. We can compute the diffuse specular ambient reflection from some illumination model and blend the texture color with it, or directly use the texture color as the diffuse reflectance coefficient. And there are different ways to do sampling, MIP mapping. I'm going to talk about these MIP mappings and aliasing things on Thursday. So let's continue these texture slides on Thursday. And also we are going to start frame buffer objects on Thursdays, which will allow us to do rendering, either the color buffer or the depth buffer, onto separate frame buffer objects that are not shown on the screen. With the help of frame buffer objects, we'll be able to have dynamic shadows in our scenes. All right. So actually, I already provided one of the examples, the terrain, the visibility, terrain visibility example that I shared with you. It actually uses frame buffer objects in it. So when we render the depth image from the perspective of that other camera, you're actually rendering on a separate frame buffer, and we are using the depth value of that camera's point of view to render some parts red, some parts green. All right, so we are going to talk about those on Thursday. That's it from me for today. See you all on Thursday. All right, bye bye. I'm going to stop the recording now. İyi günler.